The next order of reaction we're going to discuss is first order. So in first order reactions, what we see is if the concentration is doubled, then the rate of the reaction also doubles. Okay, so for first order, we can talk about K. So if we think about this, okay, so rate would be equal to K times the concentration, and we're just going to use A as our example to the first order. So let's plug in units. We know for rate, it would be moles per liter times seconds. Okay, so again, this moles per liter is my molarity. Okay. We know A would have concentration of moles per liter, and it's to the first order, so those would be my units. So I can clearly see that the mole unit appears on both sides of this equation. The liter unit appears on both sides of the equation. And so the unit that we're missing is seconds, but notice it's on the bottom of my ratio. So we would say that K is seconds to the negative first power. Okay, so let's look at the graph that's going to give me a linear relationship. So in this case, it's going to be the natural log of our concentration. So again, I'll just be generic and use A, even though here we can see it's N2O5, okay, versus time. Okay, so again, we're going to derive our integrated rate law equation. So we're going to use the equation of the line. So y we can clearly see is the natural log. And again, I'm just going to be generic and use A. Again, we can see our line is decreasing, so it's going to be a negative slope. And the slope here is also going to give us our rate constant. X is time. Now in this graph, time is very specific. It says seconds, but again, it could be minutes also. And the y-intercept here would be the natural log of our reactant initially. All right, so we can use our integrated rate law equation to come up with our half-life equation. So I'm going to rewrite our integrated rate law equation. All right. So again, if we're talking half-life, then it's half the original concentration. And again, I'm going to move this KT to the other side so that it's positive. All right. And I'm going to move this natural log of A initial over 2 to the other side. So it looks like this, the natural log of A initial over A initial divided by 2, so that it actually looks like this. And I can see that these A initials are going to cross out here. And so what I really have is I have the natural log of 2 here, and the natural log of 2 is 0.693 is equal to kt. And again, we want t by itself, so we're going to divide both sides by k. So the half-life for first order is equal to 0.693 divided by k, which is our rate constant. All right, so those are our equations for the integrated rate law. And so once we've talked about all the rate laws, we'll come back and we'll solve some problems.